Bawdsey Manor, 1936. Britain was standing on the edge of a disaster it could not see coming. Across the Channel, German factories were producing faster, deadlier aircraft, and every expert in London understood a truth the government could not publicly admit. If those bombers crossed the North Sea, Britain had no reliable method to detect them early enough to respond. Searchlights failed in cloud or darkness. Acoustic mirrors were crippled by wind and terrain. The sky was becoming a battlefield, and the nation was blind. Amid this uncertainty, an engineer emerged with an idea that sounded more like speculation than strategy. Not a new weapon, not a faster fighter. A scientific method to turn invisible radio waves into vision. That engineer was Robert Watson Watt, a mathematician whose notebooks were filled with equations on wave behavior, reflection geometry, and atmospheric interference. Watson Watt was not thinking about building more aircraft. He was thinking about time. If Britain could see incoming bombers minutes earlier, those minutes could be turned into organised defence rather than chaos. He began by studying what radio waves could reveal. Long wavelengths travelled immense distances and reflected off aircraft, but only if the right pulse length, frequency stability, and antenna configuration were used. Watson Watt calculated how transmitted pulses would decay, how reflections weakened with distance, and how variations in pulse repetition rate affected detection clarity. His analysis pointed toward a radical conclusion. With the correct engineering approach, returning echoes could reveal altitude, distance, and bearing. The sky could be mapped using mathematics, but equations alone meant nothing without proof. The Air Ministry had heard too many impossible ideas. They demanded a demonstration. On a freezing February morning near Daventry, Watson Watt and his assistant Arnold Wilkins assembled a crude experiment using transmissions from a BBC shortwave station. Their equipment was basic, but the physics was precise. As a Royal Air Force bomber passed through the radio beam, the oscilloscope spike was unmistakable. A moving aircraft had been detected using radio reflection alone. Britain had just taken its first step toward an entirely new kind of defence. The demonstration forced immediate action. Watson Watt was transferred to Bawdsey Manor, a small coastal facility that became the headquarters of Britain's secret electromagnetic research. There, he gathered a team of physicists, engineers, mathematicians, and technicians around a single objective: transform that fragile experiment into a continuous coastal defence system. The first obstacle was range. To detect bombers far out at sea, transmitters needed high power, stable pulses, and antennas mounted on towers over 100 metres tall. Watson Watt oversaw calculations defining effective radiated power, free space loss, and propagation over curved terrain. Each variable influenced how far a radar station could see, and margins for error were small. Next came altitude measurement. Knowing that aircraft were approaching was insufficient. Fighter command needed to know how high they were flying. Watson Watt worked on phase comparison techniques using vertically separated antenna arrays. By measuring amplitude differences between signals, operators could estimate altitude with surprising accuracy. This innovation turned radar from a warning tool into a tactical asset. Interceptors could climb to the correct height before the enemy arrived, conserving fuel and maximizing strike potential. As stations were built along the coastline, reliability became the dominant challenge. Radar had to work in storms, heat waves, freezing nights, and atmospheric distortions. Watson Watt insisted on rigorous testing under real coastal conditions. Equipment was moved between fields, cliffs, and marshes to analyze environmental effects on signal strength. Each test refined the pulse shape, filtering methods, and synchronization systems. Slowly, a network began to emerge. It would later be named Chain Home, but at this stage it was simply a race against time. By 1937, test flights revealed how much had been achieved. Aircraft flying far beyond visual range appeared clearly on oscilloscope screens. Operators learned to distinguish formation movements, altitude trends, and speed variations. The system's range expanded steadily as engineers improved the transmitter stability and receiver sensitivity. Chain home was no longer an experiment. It was becoming a strategic necessity. The Air Ministry, initially sceptical, began to recognise its value. Radar provided something Britain had never possessed in past conflicts: predictive control. Instead of reacting blindly to sudden attacks, Fighter Command could now prepare interceptors before enemy aircraft approached the coast. Watt refined communication protocols linking radar data to centralised plotting rooms, ensuring that information moved efficiently across the command network. Radar was evolving into the backbone of Britain's air defence. Yet the threat was escalating faster than the technology. Germany was building long-range bombers capable of carrying heavier payloads. Britain could not match these numbers through aircraft production alone. Radar was the multiplier Britain relied upon. It turned limited fighter resources into a coordinated force guided by real-time information. Watt understood that every minute gained through detection reduced casualties, preserved airfields, and strengthened national resilience. By early 1938, Britain finally possessed a shield extending across its eastern coastline. The system was imperfect. It lacked fine resolution, struggled with low-altitude targets, and required constant calibration. But it existed. No other nation had anything comparable. Radar was no longer a theoretical curiosity. It was becoming the first layer of defence, in a war that seemed increasingly unavoidable. Before we continue, feel free to like and subscribe if you appreciate accurate, engineering-focused documentaries. How would Watt and his team transform this early system into the operational network that defended Britain once war arrived? When Europe descended into war in 1939, Britain entered the conflict with a tool no enemy fully understood. Watt's early stations were operational, the personnel were trained, and the infrastructure linking radar sites to Fighter Command had taken shape. But the system had never been tested under continuous pressure. Britain relied on a chain of steel towers, synchronized transmitters, fragile receivers, and operators interpreting faint echoes on dim screens. These components formed a defensive machine that needed to prove it could coordinate an entire nation's reaction to aerial assault. The first German incursions were small reconnaissance flights that revealed the network's potential. Radar detected aircraft long before they approached the coastline, giving Fighter Command time to analyse formation patterns, altitude changes, and course adjustments. Each detection passed through filter rooms where teams converted raw signals into plotted tracks. This information moved to the command centre, where controllers assigned squadrons based on distance, fuel, and combat readiness. For the first time in military history, air defence became data-driven. The sky was no longer interpreted visually but mathematically. Watt's design philosophy became immediately visible. He had insisted on standardizing calibration across stations, ensuring that pulse power, frequency stability, and antenna alignment matched from site to site. This uniformity allowed signals from different stations to be compared accurately, forming a coherent picture of the battle space. Without this discipline, tracking multiple aircraft would have been chaotic. Instead, the network functioned as a unified sensor grid, capable of guiding interceptors with increasing precision. As German activity intensified, the system faced more complex challenges. The Luftwaffe began sending multiple formations simultaneously, separated by altitude and distance to confuse defenders. Chain home tracked each formation, distinguishing major bomber groups from escort fighters based on echo strength and flight behaviour. Radar operators learned to identify target types through signal characteristics. Heavy bombers reflected stronger pulses, while fighters appeared as smaller, more erratic traces. These distinctions mattered. Fighter Command needed to know where to concentrate resources, and radar provided the clarity needed to avoid wasting fuel on decoys or minor threats. During early 1940, experiments pushed the system further. Test flights evaluated how radar responded to rapid altitude changes, steep dives, and formation splits. Operators practiced maintaining contact with aircraft, moving at increasing speeds, adjusting gain settings to prevent targets from vanishing into clutter. These drills revealed weaknesses. Chain-home struggled with low-altitude detection, and atmospheric conditions sometimes distorted signals. Watson Watt recognized these limitations immediately. Instead of attempting to alter the original design, he directed efforts toward complementary systems. Chain-home low began to emerge, providing coverage closer to sea level. Mathematical models refined altitude estimation, and filtering methods improved clutter separation. Each enhancement strengthened the broader network without undermining its core structure. By mid-1940, the Luftwaffe launched sustained attacks. Radar's value expanded dramatically. Stations detected enemy aircraft crossing the channel, tracked formation shifts, and identified intended targets through small course adjustments. Fighter Command used this information to vector squadrons efficiently, eliminating the wasted patrol flights that had drained fuel in previous conflicts. Pilots no longer searched blindly. They climbed to specific altitudes, turned toward precise vectors, and arrived directly in the path of incoming bombers. The efficiency of this process helped compensate for Britain's numerical disadvantage. Germany possessed more aircraft, and many were faster or more modern. But Britain possessed a network that multiplied the effectiveness of every fighter. Radar created time, and time became strategic leverage. Squadrons could refuel, rotate pilots, and repair aircraft without fear of surprise attack. Airfields remained operational. Ground crews worked methodically, and the country maintained control despite facing a larger force. As the attacks intensified during the early phases of the Battle of Britain, Chain-home endured significant stress. Stations ran continuously, oscilloscopes flickered under heavy loads, and transmitters overheated. German aircraft attempted to suppress the network by targeting radar stations directly. Bombs damaged towers, ruptured cables, and disrupted power supplies. But the system had been designed with redundancy in mind. Backup generators, duplicate transmitter rooms, and alternative signal lines ensured rapid recovery. Technicians worked through bombardments to restore functionality, reflecting the engineering resilience Watson Watt had demanded from the start. Early in the battle, Germany attempted to exploit perceived blind spots by approaching at very low altitude. Chain-home low mitigated much of this threat, and ground observers from the Royal Observer Corps covered areas beyond radar coverage. The integration of these visual reports with radar tracks provided additional verification and reduced the risk of false alarms. Radar took the lead, but it was part of a layered system that functioned with increasing cohesion. The Luftwaffe eventually shifted tactics, launching widespread attacks across southeastern England. Chain-home tracked the density of formations, revealing when bomber groups thickened or dispersed. These shifts indicated staging maneuvers, refueling patterns, or target changes. Fighter Command used this information to prioritize intercepts, protecting critical infrastructure, factories, and airfields. Radar did not shoot down aircraft, but it ensured that the right aircraft were in the right place at the right time. Operators became experts at interpreting fluctuations in signal amplitude caused by weather, relay interference, and multiple reflections. This expertise, combined with consistent engineering upgrades, allowed the system to withstand German attempts at radio jamming. Interference patterns themselves provided useful clues. When signals were disrupted in specific frequency bands, operators deduced approximate bomber locations using the direction and intensity of the jamming. Radar had become so fundamental to British defence that even enemy countermeasures generated additional data rather than confusion. By late summer 1940, radar was woven into every major decision made by Fighter Command. It shaped squadron allocation, interception timing, and defensive planning. Without it, Britain would have been forced into reactive, disorganised defence. With it, Britain maintained control of its airspace despite overwhelming odds. The early war years proved one fact beyond debate. Watson Watt had not merely invented a tool, he had engineered a system that reshaped modern air defence. The next phase of the war would push this system into maritime operations, night fighting, and offensive coordination. But its foundation was already established, a network built on precision, standardization, and the analytical discipline that defined Watson Watt's work. How would radar evolve when Britain expanded its use beyond simple detection and into a technology that influenced multiple dimensions of the war? As the war intensified, radar no longer served only as a defensive shield. It became an engineering platform that Britain adapted to new environments, new threats, and new tactical requirements. Watson Watt understood that the conflict had entered a phase where air defence alone could not determine victory. Radar needed to evolve into a family of systems operating across land, sea, and air. Each environment imposed different constraints on frequency, antenna design, power output, and signal processing. These challenges pushed British engineering into territory few had anticipated before the war. The first major expansion came in night fighting. German bombers shifted their operations to darkness, hoping to bypass Fighter Command's response network. Chain-Home could detect aircraft at long range, but interception in darkness remained nearly impossible. Britain needed radar not only to track bombers from the ground, but to guide fighters directly to their targets. This demanded airborne radar. Early attempts faced significant obstacles. Aircraft vibrated violently at high speed, causing receivers to drift off frequency. Temperature fluctuations altered signal stability. Space was limited, requiring compact transmitters, lightweight antennas, and resistive components that could withstand rapid altitude changes. Engineers focused on miniaturizing high-frequency equipment. Advances in magnetron technology provided the breakthrough. The cavity magnetron produced powerful centimeter wavelength signals, allowing for smaller antennas, narrower beams, and greater resolution. This transformed airborne radar. For the first time, night fighters could detect enemy bombers at several kilometers, track them through cloud or darkness, and close in for interception, guided by precise electronic information. Watson Watt's early principles of wave propagation remained at the core, but the technology now entered an entirely new domain. Britain began deploying radar-equipped aircraft specifically designed for nocturnal combat. The Luftwaffe quickly realized that darkness no longer guaranteed safety. Simultaneously, radar became essential to Britain's naval survival. German U-boats threatened supply routes across the Atlantic, placing immense pressure on convoy operations. Surface scanning radar allowed ships to detect submarines at periscope depth, identify surface raiders, and spot incoming aircraft. These maritime radar sets required robust waterproofing, stabilized mounts to maintain beam direction in rough seas, and filtering techniques to differentiate targets from sea clutter. Watson Watt's understanding of reflection patterns proved invaluable in refining these systems. Engineers learned how saltwater, wave motion, and horizon curvature affected propagation, leading to improved algorithms for target identification. This shift altered the balance of naval warfare. Convoys gained situational awareness that denied submarines the advantage of surprise. Ground operations saw similar advancements. Britain needed radar to support anti-aircraft artillery, which relied on predicting aircraft paths with high precision. Engineers developed gun-laying radar capable of tracking targets in real time, calculating future positions based on velocity and trajectory. These predictive models required rapid signal processing and stable communication links between radar units and gun batteries. Watson Watt's mathematical approach to timing and wave behavior shaped the system's accuracy. By integrating radar into artillery operations, Britain increased hit probability against high-speed targets and reduced ammunition waste. Anti-aircraft units became more efficient, protecting industrial centres and ports from sustained bombardment. the engineering challenges extended even further. Mobile ground forces required transportable radar systems. These needed lightweight components, collapsible antennas, and power supplies capable of operating in unstable environments. British teams developed mobile radar units that could be assembled quickly, calibrated in the field, and operated by small crews. These systems supported advancing troops, provided early warning for isolated positions, and offered detection capability during rapid maneuvers. Watts and Watt's push for standardization made mobility possible. Modular components, unified training, and consistent signal interpretation allowed radar operators to deploy technology wherever the war demanded. By 1943, radar had become a foundation for offensive operations as well. Bombing raids over Europe required precise navigation through poor visibility and unpredictable weather. Radar navigation aids allowed pilots to reach targets accurately even when blinded by cloud or darkness. Ground mapping radar gave aircraft the ability to identify coastlines, rivers, and urban patterns using reflected signals. These systems used principles Watts and Watt had championed years earlier: reliable timing, stable frequency control, and predictable reflection analysis. Aircrews could strike strategic targets with increased accuracy, expanding Britain's reach and diminishing Germany's confidence in weather-based protection. Radar was also used to mislead the enemy. As the Allies prepared for major offensives, including large-scale landings, radar deception became an essential tool. Engineers created false signatures using controlled transmitters to simulate phantom fleets or aircraft formations. These operations required deep understanding of enemy radar interpretation methods. Watts and Watt's analytical framework influenced the deceptive tactics that manipulated German strategic planning. Radar had evolved from detection to deception, giving Britain an advantage in psychological and strategic dimensions of warfare. As radar expanded, Watts and Watt faced a new challenge: organisation at scale. Research teams worked across dozens of sites, each developing specialised systems. Coordination required unified technical standards, continuous data sharing, and rapid distribution of improvements. Watts and Watt provided the leadership necessary to maintain coherence. His discipline in applying physical law, verifying results experimentally, and standardizing processes ensured that the system remained integrated across domains. Britain's radar capabilities grew broader, more precise, and more resilient as a result. By the later stages of the war, radar permeated every aspect of British military strategy. It guided fighters, protected convoys, directed artillery, supported bombing raids, and influenced deception operations. The Luftwaffe faced a defensive network and electronic environment far more complex than anything Watts and Watt had built in 1936. Radar had reshaped air combat, naval warfare, and ground operations. It transformed the war from one dominated by visual observation to one governed by electronic awareness. Before we continue, feel free to like and subscribe if you appreciate engineering-driven historical documentaries. How would Watts and Watt's radar legacy influence Britain's transition from wartime innovation to peacetime technological leadership? As the war ended in 1945, radar stood as one of Britain's most decisive scientific achievements, and Watts and Watt's influence was woven through every layer of it. The technology had evolved far beyond the crude oscilloscopes and experimental towers of the mid-1930s. It had become a complex ecosystem of high-frequency transmitters, precision antennas, airborne systems, maritime scanners, and predictive models that shaped the outcome of the conflict. But peace introduced a new set of challenges, transitioning radar from wartime urgency to long-term national development, restructuring scientific institutions, and defining how this technology would guide Britain into a new era of electronic innovation. The first transformation occurred within military infrastructure. Wartime radar had been functional, fast, and adaptable, but it was also improvised. Equipment was built under pressure, field repairs were constant, and many systems operated beyond their intended lifespan. Post-war planning demanded refinement. Britain sought to modernise its radar network with improved frequency stability, longer operational ranges, and more reliable components. Engineers replaced wartime vacuum tubes with more resilient designs, refined transmitter circuits, and added automated calibration to maintain accuracy across large geographical areas. Watts & Watt's engineering philosophy remained the guiding framework. Data must be measurable, systems must be stable, and technology must obey physical law with precision. Maritime defence underwent similar modernisation. During the war, ship-mounted radar had evolved rapidly, but the post-war Navy required systems capable of detecting faster aircraft, smaller vessels, and emerging submarine technologies. Advances in magnetron design allowed higher resolution imaging, enabling ships to track threats in cluttered coastal waters. Engineers analysed sea state reflections, atmospheric ducting, and duct layer interference to refine maritime algorithms. Watts & Watt's early research into propagation over water informed these developments. His understanding of how wave behaviour shifted with temperature, humidity, and sea surface conditions became a reference point for the next generation of naval radar systems. Civil aviation emerged as another priority. Radar had proven its value in controlling fighter movements, but peacetime demanded tools for navigation, traffic monitoring, and collision avoidance. Airports required systems capable of guiding aircraft safely through fog, storms, and crowded airspace. Engineers adapted wartime ground mapping techniques to civilian air traffic control, integrating precision approach radar and long-range surveillance systems. These technologies created safer flight corridors and reduced the margin for human error. Watts & Watt's insistence on standardized calibration and signal interpretation shaped the protocols used to train radar operators and unify civil aviation procedures. Scientific research expanded rapidly as peacetime funding became available. Universities and laboratories across Britain established dedicated radio physics departments, many staffed by engineers who had trained under Watts & Watt during the war. The discipline he instilled, rigorous testing, controlled experimentation, and a mathematical approach to electromagnetic theory, now guided civilian innovation. Radar principles influenced telecommunications, weather forecasting, maritime navigation, and early computer science. Britain invested in research structures that allowed these disciplines to grow, linking industry, government, and academia more closely than before. Industrial applications soon followed. Radar-inspired technologies provided foundations for advanced measurement systems, distance-ranging equipment, and automated detection tools used in mining, oil exploration, and civil engineering. The concept of using reflected signals to map hidden structures extended beyond aircraft detection. Scientists applied similar methods to geological surveys, atmospheric studies, and even medical imaging in early exploratory work. Watts & Watt's legacy shifted from a purely military domain to one that supported national industry and scientific advancement. International collaboration became another critical area. Radar had reshaped alliances during the war, and it continued to influence geopolitical strategy afterward. Britain contributed to joint research initiatives with the United States and Commonwealth nations, sharing data on propagation, magnetron design, and signal processing. These collaborations strengthened NATO's early warning architecture and created unified detection standards across member states. Watts & Watt participated in advisory roles, providing technical assessments that helped integrate British radar expertise into global defence planning. Despite his accomplishments, Watts & Watt remained deeply aware of radar's limitations. Cold War tensions introduced new threats: high-altitude bombers, jet aircraft, and missile systems that travelled faster than anything seen in the early 1940s. radar needed to adapt again. Britain invested in early warning systems capable of tracking long-range bombers approaching from the Arctic, requiring massive installations, improved pulse compression, and more sophisticated filtering techniques. Watt's foundational research still guided these expansions, even as new technologies emerged to meet the challenge. The development of missile detection represented an even greater leap. Ballistic missiles travelled at extreme speeds and altitudes, demanding shorter wavelengths, faster sweep rates, and more advanced signal processing. Britain built upon the mathematical frameworks Watt had established, integrating high-frequency radar into broader early warning networks. Engineers studied ionospheric interactions, radar cross-section behaviour, and high-energy reflection patterns, all extensions of principles Watt had mapped decades earlier. Innovation continued in civilian technology as well. Weather radar evolved rapidly, using reflection patterns to identify storms, precipitation levels, and atmospheric disturbances. These systems improved forecasting accuracy and provided essential data for aviation and maritime safety. Radar principles found applications in ground traffic monitoring, railway safety, and early automation systems. Watt's impact extended far beyond the laboratories and airfields where his ideas first took shape. As the Cold War advanced, Watt remained a central figure in Britain's scientific community. He advised research councils, contributed to policy development, and supported the expansion of engineering education. His leadership influenced generations of physicists and engineers who would carry radar technology into new fields. By the time he stepped back from public service, radar had become a standard component of global defence, industry, and science. His work had transformed warfare, reshaped communication, and redefined what a nation could do with information. The final measure of his legacy lay not only in the towers of Chainholme or the airborne sets that guided night fighters, but in the scientific culture he helped build. Watt had shown that disciplined engineering, grounded in measurable physics and experimental rigour, could alter the course of history. Radar had given Britain the time it needed to survive its darkest hours. Its evolution afterward demonstrated how a single technological breakthrough could reshape a nation's strategic identity. As Britain moved further into the Cold War, confronting new threats and new technologies, one question remained central. How would the principles Watt established continue to guide the engineers who inherited the electronic battlefield he helped create